And in this lesson, we'll talk about vertical motion, and it's a we've seen vertical motion problems since Algebra 1, but we're just going to see how calculus can be used with vertical motion, or how it is used. So before we start, let's see that just because we see the same shape, the same parabolas in each graph, pause the video and try to describe the path of each object. So each of these graphs shows two different objects moving. So think of what each object is doing. So pause the video and try that. Now, this is the type of graph that we'll be working with in vertical motion problems. We won't be working with this because this shows horizontal motion and vertical. So the object is actually moving horizontally because it moved 5 feet horizontally and 10 feet vertically. So this could be like the side view of watching a ball go up and come down over a distance in a field. And here we just know that the ball went up to 10 feet and came back down. We don't know if it traveled horizontally, and it doesn't matter if it does move horizontally in this situation because we're just looking at its vertical position over time. So here's something interesting about vertical motion. And if there's maybe in a shooting competition, there's a rifle and the shell falls out after the bullet is fired. And so the question is, what will hit the ground first? And the rifle is shot horizontally. The bullet is fired horizontally, and the shell falls straight out. It doesn't go up and then come down. So it turns out that they will hit the ground at the same time because the bullet has horizontal velocity, but right when it leaves the barrel, it's falling. So the bullet will fall, and it'll hit the ground at the same time that the shell hits the ground. So that's an interesting physics fact. If we don't pay attention to aerodynamics, but if they're just falling through the air, they would hit at the same time. All right, one challenge with vertical motion problems is the variation, the possibility for variations in the questions for situations. All right, so we could have this is height and time, and we could have an object that's moving like that. We could have an object that's moving like that, or like this, or like that. Now over here we'd say that that's the vertex of the parabola, and over here we'd say the vertex, this is not the vertex is occurring over there. So these are all time, height, and we have to connect these situations to the vocabulary used in the questions. So this could be that it is thrown or launched. It's launched, thrown, or fired upward from the ground. And this is launched upward from point above ground this object, usually they would say it's dropped because it's not thrown up or down, and then this object could be launched downward or thrown downward. So these three are the most common types of questions. And all of these situations could have horizontal velocity or not. It doesn't matter if they're moving horizontally. All right, a ball bounces upward from the ground. So let's think about which situation that is. If it has some velocity coming from the ground, we're going to look at that graph. And it's helpful to look at time, height, and velocity. Time, height, velocity. Time, height, velocity for each point on that graph, and then we can fill that in because not all of these values are written in the problem, we just have to know them. So the time when it starts we'll call 0. The height when it starts, it's on the ground, so that's 0. And the velocity when it starts is 40 feet per second, and that was given. The time when it reaches its maximum height is part of the question. If we knew the time of maximum height, we would know the time in the air because it's symmetric. We don't know that. The height, maximum height, is one of the questions. We don't know that. But the velocity, even though it's not given, we do know the velocity at its maximum height because it goes up with some velocity, slows down, stops, and then accelerates downwards, so that would be the velocity is 0. The time when it hits the ground is related to the time of maximum height, and it is the answer to this question, time in air. We don't know that. The height when it hits the ground is 0, and the velocity when it hits the ground, it turns out it will be negative 40 feet per second, the same velocity that it was released at. Position function. Here we have a formula. It's the height is equal to 1/2 AT squared plus V naught T plus H naught. All right, acceleration. That's gravitational acceleration. And that will be negative 9.8 meters per second squared, or negative 32 feet per second squared. Initial velocity, initial height. So with all these different variables, that's where there can be a lot of different questions asked, because each variable they could be asking for, that could be the unknown in the different problems. So we know we're dealing with this formula. We have some numbers to substitute, but how are we going to use this to find the time in the air? we're trying to find this, and we know that the height is 0 when time is what we're trying to find here. So we can say, well, we know the height is 0, and that's going to give us this value because this is 0 due to this. We want to find the time when this is 0. So we're going to take this and put a 0 there, 1/2, and here the question is in feet, so we need to use -32. We're going to solve for time. We have an initial velocity of 40 and an initial height of 0 because it's on the ground. -16t squared plus 40t. And we can divide by 8. We can factor. And we get t equals 0. -2t plus 5 equals 0. So t is 5/2, 2.5 seconds. So just by knowing that the object was thrown upward at 40 feet per second, we know it'll be in the air for 2.5 seconds. And it doesn't matter whether it's moving horizontally or how large it is, as long as the size doesn't affect the air resistance. Okay, let's find the maximum height. The maximum height is the vertex. So we could just use the vertex formula, but we can also use calculus and find the velocity. If we're just going to use the vertex, this is what you would do in some class before calculus. We know that we have -b/2a, and here, looking at this, b is 40, so we have -40/2. A is -16. And that's 5/4. If we substitute this time into this equation, we get 25. And that is the height when the time is 5/4, 1.25 seconds. The height is 25 feet. Now, we can do max height like this, or we can use calculus. And we're going to use calculus by remembering that the velocity is 0 at the maximum height. So we can say, let's find out the time when the velocity is 0. Velocity is going to be the derivative of this function. So we need to take the derivative of, let's just look at this. Find the derivative of that, and that'll be velocity. Then we'll find out when that equals 0. So we find h prime, which is velocity, is going to be -32t plus 40. We want to know when that equals 0. -32t plus 40 equals 0. T is going to be 40/32, or 5/8, 5/4. And that's the same thing that we found over there. Then we would find what is the height at 5/4 seconds, and that was 25. If we substitute 5/4 into this, we're going to get 25 feet. Okay, try this one on your own. Pause the video and just remember that it doesn't matter if it's thrown at an angle as long as we're given the vertical velocity. If we were given the velocity at this angle, we'd have to use trigonometry to find the vertical velocity. But we already know the vertical velocity is 80, so we can really just disregard the 45-degree angle. Pause the video and try that one. Thrown from ground level, so we know we have this graph. Find time, height, and velocity. Time, height, velocity. Time, we don't know. Height, we don't know. Velocity is 0. Time when it hits the ground, we're supposed to find that. The height when it hits the ground is 0, and the velocity is going to be negative 80. Here the velocity is 80, height is 0, time is 0. And we need to find the time that it's in the air. That's how long it takes to land, so that's what we're trying to find there. And let's use the formula. 1/2 at squared plus v naught t plus h naught. 1/2, we're dealing in feet, so we'll have negative 32 t squared. Initial velocity is 80. Initial height is 0. We want to know when the height is 0. Find time when the height is 0. Negative 16 t squared plus 80. And we can, if we weren't able to factor, then we would use the quadratic formula. Let's divide by 16. So t is 0 or t is 5. So that means the object is in the air for 5 seconds. It lands after 5 seconds. To find the maximum height, let's find the velocity function. Velocity is the derivative of this. So we'll go negative 32 t plus 80. We want to know when the velocity is 0. That will be the time at which it's at its maximum height. So we'll have negative 80 over negative 32. 80 over 32 is 10 over 4, or 5 over 2. And then we have to do h of 5 over 2, and that's going to be negative 16, 5 over 2 squared plus 80 times 5 over 2. And this gives us 100 feet. Three meters per second. Okay, a ball is thrown with vertical velocity. The vertical velocity is positive, so that's going upward from a height of 2 meters. Find the maximum height and the time of impact with the ground. Why don't you pause the video and try this one on your own. So it's not thrown from the ground. We don't start here. We start above and go down. We know that the time that it's thrown is 0. The height is given, that's 2, and the velocity is 3. The time is unknown here, the height is unknown, but the velocity is 0. And the time is unknown here, the height we know is 0, and the velocity we don't know. So to find the maximum height, time of impact. In the previous two problems, we said find the time that it's in the air. Well, this is going to be the same thing, the time of impact. So we can use the same strategy, but now we're using meters, so we'll have 1/2 at squared plus v naught t plus h naught. 1/2 negative 9.8 t squared. Initial velocity 3, initial height 2. And we want to know when the height is 0, find the time when the height is 0, and that'll be the time of impact. So here we can't factor, we'll use the quadratic formula and we'll say t is negative 3 plus or minus square root 3 squared minus 4 ac over 2a. Okay, we do all that work and we have t equals negative 0.402 or t equals 1.015. So this negative corresponds to some point over here. We're not going to go back in time, but we're going to go forward in time, and the time that it hits the ground is about 1 second. So then we'll find the maximum height, and that is when the velocity is 0. So let's find the velocity function. We could just do the derivative of this. We get negative 9.8 t. So 2 times 4.9, 9.8, plus 3. We need to know when that equals 0. We're going to go minus 3 divided by 9.8, 0.306. And the height at 0.306 seconds is going to be negative 4.9, 0.306 squared plus 3.306 plus 2. And this is approximately 2.46 meters. Okay, pause the video and try that one. So the key word here is it's dropped, and that determines which graph to use. Time, height, velocity, time, height, velocity. We know the height when it hits the ground is 0. The time we don't know. How long will it take to land? How long will it take? That's what we're trying to find. We don't know the velocity. The velocity when it is dropped is 0. The height when it is dropped is 10. Time when it is dropped is 0. So we're just trying to find time again. And we're dealing in meters, so we'll have position is 1/2 at squared plus v naught t plus h naught. 1/2. Acceleration in meters, negative 9.8 t squared. Initial velocity is 0. Initial height is 10. We want to know when the height is 0, so we have negative 4.9 t squared plus 10. When does this equal 0? Subtract 10 divided by 4.9. 10 over 4.9 is t squared. We'll do the square root and we get 1.429 seconds. If we square root, we know there's going to be a positive or negative value, but we only take the positive time. And we'll stop there.